Time for us to do some problems involving surface area, which once again means that we're going to have some square roots involved because surface area really ties back to length. So more practice dealing with square roots, which means time to really be careful with our algebra. Algebra is so important, and the way we get good is we do practice. So do as many problems as you can on your own. If you're following along with the video, make frequent use of that pause button and think, okay, let me try this problem out, see how far I can get. Hopefully, you're getting farther and farther as we move further and further into our course, and you're going to do great. You can do it. It's practice. The more you practice, the better you become. You're going to become amazing. So, let's begin today's practice. Our first problem asks the following question. Find the surface area. See, this is how we recognize a surface area problem. We look for words like surface area. I know. It's like, of course you know it's a surface area problem because today is surface area practice. But it's good to be able to say, oh, I know what I'm doing. I can see the type of problem I have. Okay, so what's our problem? Y is equal to 2 root x. And x goes from 3 to 8, and it's spun around the x-axis. So let's get a rough picture of what this looks like. So we have 2 root x. So, I don't know, something like that. And we're going from 3 to 8. So here, we'll mark this as 3. Mark this as 8. And so there's this piece right here. And pay attention to where you're spinning because it's going to be important. So we're going around the x-axis. Okay, so that's our goal. Now, what's our surface area formula? So surface area is going to be adding up, which means we integrate, a to b, 2 pi, the radius, which is how far away from where we spin, and the length, which is the length of a little piece. So the first thing we should always decide is, what are we integrating with respect to? Because we might have y as a function of x or x as a function of y. That really ties into the length part. So make sure we understand that before we try to do radius. So what's happening here? Well, our little piece is a little piece of length. We have y as a function of x. So it's a reasonable thing to say, all right, if y is a function of x, let's start by trying to write everything in terms of x. So our length here will become the square root of 1 plus the derivative of the function with respect to x squared dx. That's our length. And now the radius. Okay, this is where we have to think. So we say, look, our radius is going to be based off of how far away are you from the axis, the distance to where you're spinning. So it's this length. So you might say, well, what is that? And you might say, well, it's y. Of course, we say, well, we need to know. That's y. No. It's y is the direction. Or if you like, this is our function f of x. So this is our radius, r of x, and it's 2 root x in this case. So there we go, 2 root x. And all right, well, that's good. Now we should do some other things. F prime, what is that? Well, if this is our f of x, f prime of x, well, let's just make a note. That's same as 2x to 1/2. F prime of x, the 1/2 comes down, so that cancels with the 2. It'll be x to the minus 1/2. So we have integral a to b becomes 3 to 8. And then 2 pi, always there, 2 root x, our radius, and then the square root of 1 plus. Now x to the minus 1/2 is another way of saying 1 over the square root of x squared. And there we go. All right, so that's the integral we have to do. If we can do this integral, we're good. All right, well, let's think about it. Let's clean up the inside here. This is really 1 plus 1 over x. Now notice this is inside a square root, and that's a square root. One of the nice things you can do is if you have two square roots, you can combine them together into a single square root. So let's pull out our constants in front. So that would give us 4 pi in front, 2 pi times 2, integral 3 up to 8, and then there's going to be a single square root. We have an x from here, times, then from this part, 1 plus 1 over x, dx. Aha, okay, now we say, perfect. We see what we can do. We distribute the x through, and then we say, well, this is really 4 pi integral 3 up to 8 of square root of x plus 1. Now, instead of writing it as a square root, we'll write it in a more calculus-friendly way, x plus 1 to the half. Good. That is very calculus-friendly. Now, perfect. We know how to integrate this. No problem. No problem. This is 4 pi, and then you add 1 here because it's simply x plus a constant. So it's the same thing as if it was just x. So you would add 1, that would give you to the 3/2 power. So x plus 1 to the 3/2 power. But don't forget, you also have to divide. So divide by 3/2, which is the same as multiply by 2/3. You flip it over. So times 2/3. Evaluate 3 to 8. So we have 8 pi over 3, multiply 4 times 2/3. And then, all right, 8 plus 1 is 9. So 9 to the 3/2. Okay, and then subtract, 3 plus 1 is 4. 4 to the 3/2. Now, of course, we all know that 9 cubed is 729, but that's not the smart thing to do. The smart thing to do is say, look, square root of 9 first. So I'm going to think this as 9 to the 3/2 is really 9 to the 1/2, and then cube that. Square root of 9 is 3. 3 cubed is 27. Square root of 4 is 2. 2 cubed is 8. So it becomes 27 subtract 8. Well, 27 subtract 8, that's 19. So we have 8 pi over 3 times 19. Well, not the greatest numbers to work with, but 8 times 19 is, 152? I mean, one way you can think of 8 times 19, you can think of 8 times 20, which is 160. And you say, well, that's 1 8 too many. Pull back by 1 8. So that's 160 subtract 8 is 152. No, the 3 doesn't divide into anything. And so we end up with 152 thirds pi. Well, and there we go. There we go. There's our answer. Okay, good. That's not so bad. So it's kind of similar to what we have with the length problem. The only thing that's really different is we have sort of this extra 2 pi radius. Now, sometimes that extra 2 pi radius can be very helpful, or sometimes it can be very frustrating. It just depends. Well, we practice. We practice. All right, let's keep going, and let's do some more problems. So let's try our next problem. Find the surface area when the curve y equals root 2 x squared plus e cubed, where x goes from 0 to 1, is spun around the y-axis. Okay, well, what is that going to look like? Well, what we have, now normally root 2x squared, that's a parabola. But then we have this e cubed. Notice it's e cubed. It's not e to the x, it's e cubed. They're probably going to try to trick us with that one. So what we've done is we've taken our parabola and we've shifted it up. So we have our curve. If we start at 0 and go to 1, it's looking something like that. So that's our little piece of our curve that we're spinning. And what are we going to do? Well, we're going to spin it, pay attention, around the y-axis. So here we're going this way. All right, good. Now, what's our basic formula? We start there. We always start with our basic formula. So we have our surface area is adding up a to b, integrals about addition, 2 pi, and then we have our radius, how far we are from where we're spinning, and we have our length. And when we talk about radius and length, our basic idea is to say, look, here's what you should do. You should think of it as taking a little tiny piece. So that's our little tiny piece. So what's the length of that little tiny piece? And the radius says, look, how far is that piece from where you're spinning? That's the radius. Okay, so let's think about our problem. Now for us, we can recognize some of the pieces pretty simply. We can see A and B, 0 and 1. All right, so we know where we're going from, 0 up to 1. 2 pi, 2 pi. Perfect, easy. The radius, well, if I'm here, how far am I from the y-axis? Well, this distance is x. So the distance from the y-axis is x. So that says our radius here will be x. Now the length, well, that's going to be, well, I should have been careful here. Before I put x, what should I have done? I should have said, what are we integrating with respect to? And oftentimes that's the length that does that. But I looked at this and said, look, y is a function of x, so we should work in terms of x. So our length would be the square root of 1 plus the derivative squared, dx. So the dx actually is part of the length portion. Okay, so what's our derivative? Well, square root of 2, and then the derivative of x squared would be 2x. And notice the derivative of e cubed is 0. So that doesn't even show up. All right, so there's all our pieces. All right, well, good. Now we have all our parts. Let's clean it up and rewrite it. So integral 0 to 1, and then we have 2 pi times x times the square root of 1 plus, here, square root of 2 times 2, and then square that. Well, that'll be like 2 times 4, so that makes 8 x squared. And then we have to do dx. Okay, now we start saying, all right, how do we deal with our square root? Now this is a case where there's not a perfect square inside of the square root. If we didn't have that x there, we'd be like, a lot of work lays ahead for us. But we have that x there, and we ask, is there a good way to use that x to our advantage? And in this case, there's a great way to use that x to our advantage. We can do some substitution. So let's think about our substitution. We can look on our inside here, because after all, substitution is an inside job. And we say, well, on the inside, we'll let that be u. U equals 1 plus 8x squared. Then du, well, the derivative of 8x squared, 16x dx. Now, there's not a 16 there, so what we'll do is we'll just move the constant around. So I'm going to take that 16 and move it over to that side. So 1 over 16 du is x dx. And now we're in great shape. So we have, this is the integral. The 2 pi will stay as 2 pi. The x dx becomes 1 over 16 du. And this square root of 1 plus 8x squared becomes u to the half. Aha! This is looking like a reasonable integral, the kind of integral that we're happy to do. Now there's still one more part we have to look at. Don't forget the bounds. You should always update the bounds as you go. So you should always be moving forward when you think about updating the bounds. You know, if you make a substitution, update the bounds. And the nice thing is, you never have to go back. It makes things so much simpler if you don't have to go back. So these are x bounds because it's attached to the dx. So we say this is x equals 0. Well, what would correspond to u? Well, plug in x equals 0 into the relationship, and you get u equals 1. Now, how about here? Here we have x equals 1. Plug it into our relationship. 1 plus 8 times 1 squared would be 9. And there we go. And 1 and 9 are kind of nice numbers because we see there's a square root involved. And so, aha, 1 and 9. It's almost like they wanted us to have nice numbers because they wanted us to have nice numbers. Ah, these problem writers, they're such kind-hearted people. Okay, so what do we have here? Well, 2 times 1/16, that's 1/8. Then there's a pi, so I'll write a pi over 8 in front. Integral of u to the 1/2, u to the 3/2, and then we're going to put a 2/3 in front. Because remember, flip it over. All right, and evaluate that from 1 to 9. Well, okay, you can do a little bit of cancellation. The 2 and the 8 cancel, leaving you with the 4 downstairs. And 4 times 3 is 12. Okay, so that's good for us. So we really now have pi over 12. And then we have 9 to the 3/2. Subtract 1 to the 3/2. Almost a little bit of deja vu. Well, 9 to the 3/2 we talked about. Square root of 9 is 3. 3 cubed is 27. 1 to the 3/2 is 1. It's kind of easy to work with. So we end up with pi over 12 times 26. Well, these are both even numbers. So let's go ahead and divide out by a 2. And if we do that, we end up with 13 pi over 6. And that's the answer. There we go. 13 pi 6 is our surface area if we spin. Now, let's, before we leave this problem, ask a simple question and see if we understand why. The question here is, why did this e cubed not really show up anywhere? Did we make a mistake, or did it not matter? What do you think? Well, think about what the e cubed does. So the e cubed is about vertical shift. So it's shifting our curve up and down. But you notice if we shifted our curve up some more, shifted it up here, so in other words, we changed, instead of e cubed, we picked a different value. If we still spun around the y-axis, it's the exact same shape as that we spun if we hadn't shifted more. So that shift doesn't affect the final figure, and therefore doesn't affect the surface area that comes out. So it's actually good that the e cubed did not show up at all. If it had shown up, we've made a mistake. And probably if it had shown up, we would have gotten stumped at some point. So that's why the e cubed doesn't matter. Sometimes you'll see little pieces and say, this is going to make things hard. But then you get into it, it's like, wait a second, you didn't need this part at all. So, take a look and pay attention. Maybe things are not so bad as they seem. All right. Well, here we go. Another problem, right? Of course. Now, our next problem. Set up, but do not evaluate integrals which find the surface area when y equals e to the x, where x goes from 0 to 1, is spun around the following. So you have the y-axis, the x-axis, x equals 1, y equals 1. Okay, so we're going to think about what our various pieces are. So it's going to be helpful for us to make sure we have a picture of what's going on in our situation. So let's do a quick sketch. Now y equals e to the x is actually not so hard to sketch. What does it look like? Well, it starts, e to the 0 is 1. So let's say this is 1 here. And then it's going to go up. And so this is here. Here's e, here's 1. And then down here, this is 1. All right. So let's get into it. So our basic formula is going to be the same all the way through. So we have that surface area is equal to, and notice that we have a function of e to the x, so we're going to be thinking of that, adding up 2 pi, our radius, and our length. So we say, well, look, 2 pi, we know the length, thinking of this as a function of x, well, that would be the square root of 1 plus e to the x squared. Now this e to the x is not that e to the x. You probably think, wait a second, what? What it is the derivative of e to the x is e to the x. So this is the derivative of that function. So there was a derivative involved there, and dx. And our bounds, well, those are pretty simple. Those are going to be 0 and 1. So what we really have here is that our surface area is the following. It's 0 to 1 of 2 pi. Then there's something here. And then there's the square root of 1 plus e to the 2x dx. Where this box, what's that box? That box is the question, how far to where you spin around. So now we really can say, look, for us to finish this problem of setting up, all we have to ask is, what's in the box? What's in the box? So that's our goal. What's in the box? So we have to think about it. So here, this is the part that varies. As we go through these 4 parts, none of the rest changes. So the answers are going to look amazingly similar to each other. It's just this is what we have to figure out. So this is what's going to figure out what's in our box. Now, with that in mind, we can go through and start thinking about our problem. So here's the thing. We always think about spinning a little tiny piece. So here's my little tiny piece. And now we go through and say, let's figure out our distances. So we'll do it one at a time. So for part A, well, we're going around the y-axis. If we go around the y-axis, that says we're going over to here. That's the y-axis. So what's my distance from a point? And really, if you like, you can think of this as a point as x comma y. So what's this distance here to the y-axis? Well, it's the x value. X is how far off the y-axis we go. Okay, so that means that what goes in the box is x. Good. So integral 0 to 1, 2 pi x, square root 1 plus e to the 2x dx. Okay, there we go. Part A, done. Now, let's go and talk about part B. So for part B, what's happening? We're going to the x-axis. So we go down. We say, all right, if we're going down to the x-axis, how far is it from this point to the x-axis? Well, you might say, why? And my response is, well, because we need to know. And you're like, no. Why the variable? Oh, the variable y. Of course it is. Right. If you think about your coordinate, y is how far away you are from the x-axis. Now, we have everything in terms of x. So we don't want to put y down. So we say, well, wait, y is e to the x. So this becomes integral 0 to 1, 2 pi e to the x, which acts like our y, square root 1 plus e to the 2x dx. Okay, 2 down. So we're going pretty quick here. Now, let's go to our next version. Okay, so let's do this one. The line x equals 1. So, where is x equals 1 in this diagram? Well, x equals 1 is this line right here. All right, so when we talk about going around x equals 1, that's our distance from the little part that we're spinning to x equals 1. Now, what is that distance? Perhaps we should step back and say we've been a little bit cavalier about our radiuses. So let's pause for a second and remind ourselves that when we talk about radius, we're really talking about some type of a measurement. A measurement is involved at some point. And whenever we have a measurement involved, well, that measurement should be positive. So we're a little bit just like, oh, it's just x, it's just y. Well, because in our diagram, x and y were positive. So here it's a little bit more subtle. So the question is, I'm going here from x over to 1. Well, what is that distance? Now you have to be careful. Now, is it x minus 1 or is it 1 minus x? So there's two choices. Now, what's the difference? Well, the difference, it really just comes down to the sign, but we want to make sure we get a sign right. A surface area should be a positive number. So in our case, we say, well, look, 1 is larger value. So we're going to take the right minus the left, high minus the low. So high minus low means that this length is 1 minus x. So for part C, we get the integral 0 to 1 of 2 pi, and our radius, what goes in the box? 1 minus x. Square root 1 plus e to the 2x dx. One more to go. All right, so our last one, part D. Now we're going to the line y equals 1. So y equals 1 is right there. So now we ask the question, okay, how far is it down to that line? Well, similar process, so we can go ahead and put in sort of the other pieces, because they don't change, it's just that the radius which has changed. Okay, so how far is it? Well, you have high minus low. That's what we should think of. High value minus low value. So here we're at y, here we're at 1, so it's y minus 1. So you'd say, haha, this distance here, I can think of this as y minus 1. But wait a second, we can't put it in terms of y because we're integrating with respect to x. So everything has to be in terms of x. But now we remember, oh, no problem. Y is e to the x, so y minus 1 becomes e to the x minus 1. And we're done. That's it. There we go. You see, again, really, it's what's in the box. That's the surface area. What's in the box? What's in the box? How far is it from my little tiny point to where I'm spinning? Once I know that, everything else is not so bad, at least in setting it up. Carrying out the integrals. These integrals are not so pleasant. This one is almost doable. Almost. We'd probably need a few more tools to get there. But, you know, we're patient. We're patient. All right. Good. On to another problem. Okay. Find the surface area when y equals the square root of 4 minus x squared for negative 1 less than or equal to x less than or equal to 1 is rotated around the x-axis. Now let's think about what we're doing here, because I think this is going to be kind of amazing at the end. If you see what's going to happen, we're going to talk about the answer for a second. What's this curve? Y equals the square root of 4 minus x squared. Well, that's kind of a curve that we should hopefully start to learn to recognize. When you see y equals to the square root of something minus x squared, that's part of a circle. So what we have here is that there's a circle of radius 2. And really we should say, because it's the positive square root, it's the top half of the circle. So I have the top half of a circle of radius 2. All right, so there's our top half of the circle. Now we're not going to take the top half of the circle and spin it around. We're actually going to take just a part of the top half of the circle and spin it around. So we're going from negative 1 over to positive 1. So we're going from there to there. So when we spin, what are we going to form? Well, what we'll end up forming here is a shape, something kind of like that. Whoop, that's not quite right, is it? All right, there we go. Well, you can kind of see what it is. We've taken a sphere, but we haven't taken the whole sphere, okay, but we've taken just sort of like the center band of the sphere. So that's our surface area that we're after, is a small part of the sphere. Okay, so this problem is about surface area of spheres. And let's see what happens. Okay, spheres are nice. We should hope that we should get some nice answers. All right, so we start by saying, let's think about our basic setup. We have a little tiny piece, so here's our little tiny piece that we're spinning. And since we're spinning around the x-axis, our distance down to the x-axis, we can think of it as y. And if we integrate with respect to x, that becomes the square root of 4 minus x squared. So we're going to say the following. We have the surface area is found by adding up a to b, 2 pi, then you have your radius, how far you are, and then you have your length. It's our same formula. And we keep writing it down over and over again. You're probably like, yeah, why do you keep writing it down? I keep writing it down to really drill it in. So it's like, okay, this is our basic formula. Remember the basic formula. And once we have that basic formula memorized, we're good to go. No problems. No problems. Okay, so for us, our radius is y, which is the square root of 4 minus x squared. Our length, well, remember that, is the square root of 1 plus the derivative squared dx. The arc length, please write. Okay, so we're going to take some time to really dig into that. Our bounds are given to us. We're going to go -1, +1. So let's think about this piece. Okay, so our function f of x is the square root of 4 minus x squared. We'll write that for right now as 4 minus x squared to the 1/2. That makes it more friendly for doing calculus, in other words, for things like applying chain rule. So f prime of x, well, the 1/2 comes down, 1/2, 4 minus x squared to the -1/2, then do the chain rule, minus 2x. Or if you say, look, the 2's cancel, you end up with minus x over, and here you get the square root of 4 minus x squared. All right, so what do we have? Our surface area becomes integral -1 to +1. We have 2 pi square root 4 minus x squared times the square root of 1 plus. Now we need to square that. Well, that would become negative x quantity squared. The negative goes away, so it's simply x squared over 4 minus x squared dx. Now, well, we have a square root and a square root. We can combine them together into one single uber square root, one big square root. So this becomes integral -1 to 1 of 2 pi square root of, and when we multiply that through, well, we'll do it in 2 steps. 4 minus x squared times 1 plus x squared over 4 minus x squared dx. Multiply that through. You'll see the 4 minus x squared cancels with the 4 minus x squared. So we're getting -1 to 1 of 2 pi times the square root of 4 minus x squared. That's the 4 minus x squared times the 1 plus x squared, which is what happens when you multiply 4 minus x squared to the second term. And now we're like, whoa, something really beautiful is happening here. Wow, holy cow, it's amazing what's happening. Well, the x squareds cancel. And now, at this point, you're like, whoa, wait, where's the x? There is no more x. All the x's have canceled. Woohoo! Amazing. Amazing. Cool. So square root of 4 is, by the way, 2. And so we say, look, this is 2 times 2 pi makes us 4 pi. Integral -1 to 1 dx. Well, now we're basically done. We know how to integrate that. That's 4 pi times x. Evaluate from -1 to 1. And if you do this last thing, it's 1 subtract -1, which becomes 2. leaving us with 8 pi. And we're done. We're done. Now, what is this saying about the sphere? And it's saying something rather remarkable. It basically says when you're looking at this length times the radius, what happens is it all simplifies to something very, very beautiful. Indeed, if you think about what came out here, this part at the end, when you all simplified it, was 2. That 2 really was the radius. It'll happen for any sphere that you want. Now, the moral of this, and what this is demonstrating, is this really amazing property, which says the following, is if you look at a sphere, so here's our sphere, and now compare it to a cylinder, which has the same radius. So when I'm talking about a cylinder, I'm only talking about the sides of the cylinder. The thing is, these two have equal surface area. That's what the conclusion is. Because if you run through the computation, say, look, here, what we're doing is we're just integrating 2 pi times the radius over any part. And here, it's the exact same thing. And not only is it that the total surface area is the same, it says, look, if you want to look at just a part of the sphere, so you say, look, maybe I just want to do this part of the sphere. Well, that would match the surface area for that part of the cylinder. Now, from here, we're almost ready to say, well, what's the formula for the total surface area of a sphere? Well, the total surface area of the sphere is the total surface area of the cylinder. Now, the way we find that is we take the circumference on the bottom. Well, that would be 2 pi times the radius, that's the circumference of a circle, times the height of the cylinder. Well, the height of the cylinder will be twice r, because here we're going to go twice the radius. See, because think about South Pole to North Pole is twice the radius. So 2 pi r times 2r gives us 4 pi r squared. Now, I will say it can be shown by geometrical arguments that this is true, but here's a sort of a calculus reasoning that says, wow, look, there's this beautiful connection between surface areas of spheres and cylinders. Who knew? Who knew? It's really beautiful, but maybe we should have guessed it would be beautiful. After all, it is a sphere, and spheres are beautiful. All right, good. Well, I think we have time for one last problem to finish up our practice session. All right. Find the surface area when y equals 3 times square root of 3 times x to the 1/3 for 1 less than or equal to x less than or equal to some really strange number. The 13 to the 3/4 power is rotated around the y-axis. Now, when you see a terrible number like that, 13 to the 3/4 power, 2 things have happened. One thing is whoever wrote the problem is just like, I just want terrible numbers because ha 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 ha. Then the final answer will be so weird, there's no way somebody could cheat and get the final answer. Or, the way I like it, is you see a weird number at the start, something in the middle is going to make boop, and all of a sudden the weird number is just the right number you want, so that it becomes beautiful. And we get an amazingly clean answer. The kind of answer we want to go and tell our friends and family about. Like, you wouldn't believe how beautiful this answer is. And you'll say, watch this. Let me do some calculus for you. This is going to blow your mind when you see this. This is so cool. Well, let's find out which one of it is. Is it going to be like some really weird answer or some beautiful answer? We only have one way to find out. We've got to do the work. So let's start. We have our surface area formula to begin with. Our surface area is our adding up A up to B, 2 pi times our radius times our length. Now, we should think about our picture. This is y as a function of x. It's not totally clear what this might look like, but it's a cubed root of x. So it's probably looking like the square root of x. And so it's like the square root of x scaled if you were doing a rough picture. And we really just need a rough picture. Okay, so it's probably doing something this-ish. It's good enough for our purposes. We really just need intuition right now. All right, so now we say, well, we're going from 1 all the way over to this 13 to the 3/4 power. What a crazy number. What a crazy number. All right, and we say, look, what do we need to know? We really need to focus on the radius. The radius is sort of the important part in the setup here. It's true for all the problems involving surface area. So we have our little tiny piece, and we haven't marked yet where we're spinning. We're going around the y-axis. So the y-axis is over here. So our radius, well, since we're thinking of things in terms of x, our bounds are in terms of x, our function is in terms of x, this will be our distance to where we're spinning is x. Okay, great. So then our length, well, square root 1 plus the derivative squared dx. So let's take our derivative. We take the derivative. The 1/3 comes down. 3 times a third. Well, that's promising. They cancel. Then we have a root 3, square root of 3. And then we have x to the what power? Well, that would be x to the minus 2/3. We subtract 1. So minus 2/3. Okay. Whew. All right. Well, let's see what we have. Oh, and of course we should mark our bounds. 1, 13 to the 3/4. All right. So this becomes the following. We have the integral from 1 to 13 to the 3/4, 2 pi, and then there's an x, and then we have the square root of 1 plus, and then it'll be a 3 over x to the 4/3. Yes? Yes. I think it will be. Okay. dx. All right. This is maybe not so clear. It's not obvious when we look at the problem that it's going to be something we can do. But whoever wrote this problem had faith in us, so we're going to have faith in ourselves. All right, on we go. Well, what can we do? What can we do? We can simplify the inside. So in other words, we can say, look, I have 1 plus something. Let's put it into one single fraction. All right, that seems a reasonable thing to try. Okay, so adding up from 1 to 13 to the 3/4. 2 pi x. And then here, well, common denominator would be x to the 4/3. So we have x to 4/3 plus 3 over x to the 4/3. All right. Now, we say, okay, well, there's this nice property about square roots. And you see there's an x up here, there's an x downstairs. The nice property about square roots is if you have the square root of a fraction, a over b, you can really think of it as the square root of a over the square root of b. So we could say, well, let's pull this power of x out of the square root, because really we have a power of x and a power of x. We don't want to have two different powers of x. We want to combine things. So let's see what happens when their powers combine. What do we get? So we start and we combine, and we get the following. So adding up here, 13 to the 3/4. So square root of x to the 4/3 would be what? Well, you take the exponent and take it times a half. So it's currently to the 4/3 times a half would be 2/3. So we have 2 pi x, the square root of x to the 4/3 plus 3 over x to the 2/3. Now we say, look, x over x to the 2/3. Well, we have x to the power over x to the power. And there's another rule if we have, x to the power a over x to the power b, that's x to the power a minus b, right? Of course, of course. So 1, this is really x to the 1, and 2/3 means we have what? Well, 1, 13 to the 3/4. Then we have 2 pi x to the 1/3. And this square root, let's go ahead, we'll probably write it in a more calculus-friendly way. X to the 4/3 plus 3 to the 1/2 dx. All right, so now we've cleaned up. We've said, okay, let's simplify our expression. We've done some algebra. And, algebra is our friend. And hopefully it's helped us out. And I think it has here. It does seem a little bit simpler when we look at it. And if we stare at it for a while, we say, well, look, it's definitely not one of our basic 10 functions we know how to integrate. But there's something going on here. I see this power x to the 4/3 on the inside, and I see this x to 1/3 on the outside. And always in the back of our minds, we start thinking, substitution, substitution. It's one of the most powerful tools in calculus to help us simplify our problem. So we say, okay, is there a good substitution to make? Well, when you take the derivative of x to the 4/3, what will you end up with? You'll end up with some number, x to the 1/3. Right there. Almost as if they had planned for it to happen, because they had planned for it to happen. They did. Wow, this is amazing. Okay, all right. So that now it says, look, there's a substitution to make here. We'll set u to be what's on this inside. U is x to the 4/3 plus 3. Then what can we say about du? Du would be 4/3 x to the 1/3 dx. Now, we don't have a 4/3, so what we'll do is we'll do our fancy move the 4/3 across to make it a 3/4. So 3/4 times du is x to the 1/3 times dx. So what do we have here? We have the integral. The 2 pi is still going to be there as 2 pi. That doesn't change. X to the 1/3 dx. Well, x to the 1/3 dx is now 3/4 times du. We'll put the du here. This x to the 4/3 plus 3 to the 1/2. Well, that's now u to the 1/2. And don't forget the bounds. All right, so these are x bounds. So we start x equals 1. Okay, well, that's easy. X equals 1. 1 to the 4/3 is 1 plus 3 makes 4. Okay, great. 13 to the 3/4. Oh, this is going to be terrible. 13 to the 3/4 to the 4/3. What happens? You multiply the exponents together, right? Because there's this basic rule. X to the a to the b is x to the a times b. So you take the 3/4 coming from the power there, times it by the 4/3 coming from that power, and they knock each other out. So what do we end up with? We end up with 13 plus 3, giving us 16. So that's why we had to have such a terrible number. 13 to the 3/4 was terrible, so that at this stage, boop, it became beautiful. That's what happened. I can now, we see their thinking. Okay, well, clean up a little bit. The 2 can go cancel a little bit with the 4. So what do we have here? Well, we have 3/2 and the pi. That's our constant. Now, when we integrate u to the 1/2, that's u to the 3/2. But remember, we have to multiply in front by the reciprocal. So we have to multiply that by 2/3. And then we're going to evaluate from 4 up to 16. But almost as if it had been planned, notice what happens with our constants. The 3's go away, the 2's go away. Wow. So, we are so close. This is so cool. Okay, so this becomes pi. And then we have 16 to the 3/2. There, right? Minus 4 to the 3/2. Now, of course, we have to start thinking, Okay, 16 cubed. Oh my goodness, what is 16 cubed? I don't know, 4,096? Well, yeah, it is. But maybe we didn't know that off the top of our head. So we don't have to know 16 cubed, right? We can think of this as 16 to the half, or square root of 16, which should be 4. And then we cube that. So that would be 4 times 4 is 16 times another 4, leaves us with 64. So this is equal to pi times 64. Now 4 to the 3 halves, okay, square root of 4 is 2, 2 cubed is 8. All right, 64 minus 8. And 64 minus 8 is leaving us with 56 pi. Wow. That's so cool. That's so cool. Because look at how beautiful the answer is. It's like a nice whole number times pi. It's amazing. The problem looked terrible at the start, but then everything was set up so that if we were doing our algebra life, we lived a good, clean algebra life, it would work out nicely in the end. Oh, what a great problem. What a wonderful problem. A nice way to end our session. All right. Thanks for coming, and keep that practice up. There will always be more practice ahead.